Let us have a look at the first example for the ECL. For example number one, we are given the following current distribution. We have the plane of x equals to 10, carries a current of 100 milliampere per meter along z direction, while line of x1, y of -2, carries filament current of 20 pi milliampere along z direction. So the question is to determine the H field intensity at point of 432. So let us sketch these given current distributions then. So let us sketch the problem. So we have this is Z supposedly, and we have X and we have Y axis, right? So the X equals to 10 basically should be somehow located here. So that should be x equals to 10, and your area plane should be somehow look like this. That should be the plane of x equals to 10, and is given to have a current of 100 milliampere per meter. So we're going to have your current should be in this direction, supposedly. So that should be the current of Js, right, equals to 100 milliampere per meter, okay, in the direction of Z. Yeah, so that should be the Js supposedly. Yeah, because we are dealing with the surface current density. And then we are given a line of x equals to 1, y of -2. So x equals to 1 should be somehow located here, and y of -2 be located here. Yeah, and for this we can have the line should be drawn to be look like this. Okay, so that should be your filament current. Which is said to carry a 20 pi milliampere along z direction. Right, so your current should be in this direction, which is a 20 pi milliampere, okay, in a positive z direction. Yeah, so that should be your filament current. And based on these two current distribution, you need to determine the H field at this position, which is 4, 3, and 2. So 4, 3, and 2 by right should be located, let's say, this is 4, this is 3, and 2 is here. So we can have the point should be located here, yeah? Right, so that should be the point of 4, 3, and 2. Right, and for this particular case, we can see that the H field will be contributed by two different current distribution. We have the H1 and we have the H2, in which we assume that H1 is the H field intensity produced by the surface current, and the H2 is the H field intensity produced by the filament current to the point of 4, 3, and 2. So let us do it one by one. So for the H1, knowing that we are dealing with the surface current, which is infinite in area, because we are not given any area or dimension of the plane. Yeah, so we can assume that the plane is infinite in area. So for this, we can simply use the equation that we have seen previously, which is half Js vector cross the normal unit vector. Okay, and then it will give us half. So Js will be 100 times 10 power -3 in the z direction. And normal unit vector, if you base on this, we can say that normal direction should be towards negative x. Yeah, towards negative x, because your plane is at x equals to 10. Yeah, and the point of 432 is located at x equals to 4. So basically, the normal unit vector will be in the negative x direction. Yeah. So for this, you're going to have the answer will be 50 milli, and z cross negative x will give us a negative of y direction, and that should be the H field in the units of ampere per meter. Okay, so that should be the H field, yeah, that should be the H field. Right, and for the H2, yeah, for the H2, knowing that this is for the filament current, this is infinite in length. Yeah, so we can simply use the equation of I over 2 pi r direction of P straight away. Yeah, so I equals to 20 pi milliampere. So that should be 20 pi times 10 power -3. Yeah, and 2 pi r. R is a radial distance from your filament current to the point of 4, 3, and 2. So the R, we can see that the R should be somehow in this configuration, yeah, whereby we can see that the point here that will make a perpendicular distance with the point of 4, 3, 2 by right should be the point of 1, -2, and 2. Okay, so that should be the position on the line current or on the filament current that will make a perpendicular distance with the point of 4, 3, and 2. And from these 2 points, we can say that the R, the distance shall be equals to a set of 4 minus 1 squared, yeah, plus 3 minus of -2 squared, and that it will give us square root of 9 plus 25, which is set of 34. So we can see that the R should be equal to set of 34. Okay, and for the case of the phi unit vector, we have learned previously that the phi shall be then converted into the line unit vector cross the R unit vector, whereas the line unit vector is equals to the Z direction. Yeah, and the R unit vector, if we base on this point, we can say that the R shall be equals to this unit vector direction, which will give us 4 minus 1 to the direction of X, yeah, plus 3 minus -2 to the direction of Y, and divided by the length, which is set of 34. Okay, and for this, you're going to have Z in the vector, cross product with the 3 of X, okay, plus 5 direction of Y over set of 34. So the cross product for this L cross R will give us, yeah, so Z cross X will give us Y direction. So we're going to have 3 divided by set of 34 in the Y direction, okay, plus 5 over set of 34. So Z cross Y will give us negative of X. Okay, so that should be your H2. Yeah, the H2. And subsequently, we have we can see that the H vector, yeah, can be calculated by simply adding these two H field intensity that have been obtained earlier. So we can simply add those H field together. So we're going to have 50 times 10 to the -3, okay, plus 20 pi times 10 to the -3 over 2 pi set of 34, okay, and in the unit vector is this is 3 over set of 34, okay, so that should be in the Y direction. Okay, I need to put a negative sign then. Yeah, sorry for this. Need to put negative sign here. Yeah, in front of -50, in front of 50. So that should be the value for the Y in the vector. Yeah, and plus with the X component, which will be 20 pi times 10 to the -3 over 2 pi 5 over 34. Okay, and that is -X direction. So that should be your H field total in the units of ampere per meter. Right. So that's how we solve for the example number 1 here. So let's have a look at example number 2, where we are given the infinitely long solid conductor of radius A, which is placed along the x-axis. If the conductor carries current I in the Z direction, show that the magnetic field inside the conductor is given by H field of IR over 2 pi A squared in the direction of phi. Okay, so we are given this diagram with this particular problem, whereby if we can sketch the diagram, it should look like this. Okay, the radius is A, right? And this is a solid conductor which carries I, yeah, throughout the cross section of this conductor. All right. So you need to show that the H field inside the conductor is given by this. So our concern is for the region of R, the radius of R, which is less than A. So this is our main concern, yeah, the region of concern. Right. So for this, by applying the ACL, because we are given a structure of infinitely long, so we can simply use the ACL to find the H field, where we can have H dot dl equals to the I enclosed to find the H field intensity. And what we have to do for the ACL, first of all, you need to sketch the Ampere loop as usual. So the Ampere loop, you need to be based on this region of R less than A. So for that, my Ampere loop will just be look like this, which is a closed loop. Yeah, a closed loop. Yeah. So the closed loop structure is given as a circular structure in a grid dotted line. Okay. And I'm using R as the radius to represent this region of R less than A. Okay, so based on this, if you base on this ACL, the left-hand side is the integration on the loop, while the I enclosed is the current inside the loop. Okay, so from here, we can solve for left-hand side terms, in which we are going to have for left-hand side, we're going to have the H phi, the direction of phi, and the dl will be r d phi, the direction of phi. Okay, so we know that dl, which is the second step basically, the dl is the dl on this particular loop, and knowing that this is a circular structure, the dl will be equals to r d phi, the direction of phi, and for the h vector, because the dl is in a phi direction, so it must follow suit, in which it must be in a phi direction also. Yeah, and for the I enclosed, if we base on this, we know that this should be the current enclosed by this Ampere loop. Yeah, so we know that if you base on the diagram, if you have a cross section of your conductor, which is pi a squared, the current flow through it will be I. Yeah, so if you have a smaller cross section area, which is pi r squared, basically this is to be the area enclosed by the loop. Yeah, so the current enclosed should be then equals to r squared over a squared multiplied with I. So that should be your enclosed current. So I need to write it here. So we have I of r squared divided by a squared. And if we proceed further, we're going to have hp of 2 pi r. Sorry, need to have integration here. Sorry for that. So when we integrate, we're going to have hp of 2 pi r of ir squared over a squared. And following this, we're going to have hp equals to I r over 2 pi of a squared. And in terms of the vector, we are going to have h vector will be equals to ir over 2 pi a squared, direction of phi in ampere per meter unit. So that should be the H field intensity for the region of R, any position of R which is less than A. Yeah, so we have proved that the answer obtained by using our method is similar to the one given in the question here. Okay, so for example number 3, we are given a case whereby we have a coaxial cable structure carries a current of I in opposite direction in the inner and outer conductors of this coaxial cable. Assume the inner conductor to have a radius of A and the outer conductor to have inner radius of B and outer radius of C, and assume that the cable axis is along the Z axis. So let us sketch the coaxial cable structure. So we have the inner cable, and then we have the outer cable here. Okay, so that should be our outer cable. Right, so the inner cable, and then we have the outer cable. So that should be the coaxial cable, yeah. So the inner cable is having a radius of A, and the outer conductor is having inner radius of B, so that should be the B, and outer radius of C. So that should be the cross section of your coaxial cable. And it states that this cable do carries a current of I in the opposite direction. So we assume that For the inner conductor, it carries current towards a positive Z. Yeah, if you assume that Z is in this direction. So the inner conductor carries I in the positive Z direction, whereas for the outer conductor, it carries a current in a negative Z direction. So that should be the I. Yeah. Okay. So that should be the case of our problems. Yeah. So you need to basically find the H field in all regions of this cable. So if we base on this, we are supposed to have 4 regions altogether, in which those regions are R less than A, the first region. Yeah, the second region is R between A and B. Okay, the third region is R between B and C, and the fourth region is R bigger than C. So we have 4 regions altogether. Yeah. Okay, so for the first region, which is R less than A, yeah, I think I don't have to do this for you because the answer for this, the method of solving the first region should be similar to example 2 before, in which for the first region here, your H field shall be written as IR over 2 pi A squared direction of feet ampere per meter. Yeah, you can prove this. You can refer to example number 2 for the answer of H field here then. Yeah. And for the second region, R between A and B, right? If basically this is a case whereby for the second region, yeah, for the second region where we have R between A and B. Okay, so first of all, you need to sketch the Impedance loop. Okay, so let's have a look at the Impedance loop for this problem. Okay, so that should be the Impedance loop for region between A and B. Yeah. Right, so for this, when we write this, that should be the R, yeah? That should be the radius of R to represent the region between A and B. So by applying the ACL, then the H dot dl equals to the I enclosed. Yeah, for left-hand side, yeah, for left-hand side, we can simply write that the H dot dl will give us HV of 2 pi R. Yeah, because this is similar to what we have seen in the previous example. Okay, because the dl vector should be r dv direction of p, and h vector should be hv direction of p. So that should be the case. And then for the I enclosed, yeah, if you base on this diagram, you know that the current enclosed by the loop should be the I. Yeah, so I will be the current enclosed by the loop. So we can simply write that the I enclosed should be I straight away. And from here, we can write that the hv shall be equals to I over 2 pi r. And in the vector form, we have H vector should be I over 2 pi R direction of feet ampere per meter. So this is the H field for the second region, which is between A and B. Okay, right. For the third region, which is between B and C, yeah. So let us sketch the okay, let's say we have the third region here. So we have R between B and C. Okay, so first of all, we need to sketch the Impedance loop to represent this region between B and C. So that should be our Impedance loop, in which the loop must be located between B and C radius. All right. And by applying the ACL, okay, so we have H dot dl equals to enclosed current. Okay, so left-hand side will give us HV, 2 pi R as usual. So we need to concern on the I enclosed here, which is the current enclosed inside, enclosed by the loop. So inside the loop now, we are going to have 2 current distribution basically. The first one is I, yeah, because that should be the current enclosed by this loop, the outer loop. So we have I, which is directed towards positive Z. And then we have part of I, which is directed towards negative Z. Yeah, so we have the first component is positive I in the positive Z direction. And the second component of enclosed current is I, which is directed towards negative Z. But not all of this, it is only part of your current of I. Yeah. So what I mean by this is that this is your R, yeah, which is for the third region here. So we can see that the enclosed current will be the I. So this particular I is referred to this I, and we need to subtract with this particular I because we have the current which is which are in the opposite direction. Yeah. So for this second I, it should be written as I R squared minus B squared over C squared minus B squared. Okay, because this is a portion of current that is confined by this loop, second loop. Okay. Yeah. If we base on this diagram, you know that this I is flowing between the radius of B and radius of C. Okay, in which we can see that the cross section of pi C squared minus B squared will be having a current of I, which is directed towards negative Z. But now the cross section has been reduced, yeah, only between B and R. Yeah, only between B and R. So for that, the cross section is pi of R squared minus B squared, in which the enclosed current will be simply R squared minus B squared over C squared minus B squared multiplied with I. So that's why we have the current is given by this equation or terms here, which is I R squared minus B squared over C squared minus B squared. Remember that we need to have different polarity for the current because one of it is pointing towards positive Z and the other one is pointing towards negative Z. And for this, if we proceed further, we are going to have HV will be equals to 1 over 2 pi R I minus I of R squared minus B squared over C squared minus B squared. Okay, so we can write this H field in terms of the vector form, which is H field direction of V in ampere per meter unit. So that should be the answer, the H field vector for the third region, which is between radius of B and radius of C. Yeah. And finally, for R bigger than C, yeah, R bigger than C. So for the fourth region, yeah, for the fourth region, my Ampere loop should be located outside here. Okay, so that should be my Ampere loop for the fourth region, which is R bigger than C. And from here, we can deduce that the enclosed current will be equals to 0. Well, the enclosed current will be equals to 0 because the I and the R will be cancelled out with each other. And as such, we can see that the H field intensity will be simply equals to 0 because there is no enclosed current. So when there is no enclosed current, the H field intensity will lead to 0 value.